I'll be presenting Word2Sense, a new embedding technique which is a joint work with my co-authors Harsha, Simhadri and Chiranjib Bhattacharyya from Microsoft Research. So, what's an embedding? It's a representation that's understood by machines, and if it's understood by humans, it is called interpretable embeddings. Now, the use case of an interpretable embedding is that we can trace what a machine or an algorithm does on our corpus. Okay, so what is Word2Sense? Now, it is a representation of the word in terms of its all senses in the corpus. For the time being, you can think of the sense as some high level meaning that a human relates to when he sees a word. For example, when you have the word bat, it's a polysemous word, that means it has multiple meanings in the corpus. It can act as an animal, it can act as a tobacco company, or it can act as a sporting sense. So what I can do is I can take a vector, a unit L1 norm vector, where each dimension represents a sense and it contains non-zeros only in relevant senses, and the number in each dimension represents the likelihood that the word is going to take this meaning in the corpus. Okay, so why are you even caring to give a new embedding? For example, the single prototype embeddings like the Word2Vec and glove has this issue that if I give you a single Word2Vec vector of the word bat, then I can't say that if it means actually an animal sense or the sporting sense, right? And people have actually tried to extract this information from single Word2Vec vector, but the issues are basically twofold. First, the assumed generative model doesn't work in larger scale, and second, even if the heuristics work, you can't explain why they work from the Word2Vec origin. Okay, and also some extra computation is needed to form interpretable embeddings from the Word2Vec embeddings. For example, spine and SPOF. So naturally people went to multi-prototype embeddings where they give multiple representations for a word representing multiple senses of a word. Now the issue was simple, it was computationally expensive, so people went for heuristics like they restricted the vocabulary, or they restricted the number of prototypes to 2 or 3 learned per word. Obviously both of them have their own caveats, and I will discuss later in my experimental section. So what are we actually proposing to do? We are saying that look, we'll share the senses among the words. What I mean is this: we'll define a sense as a distribution over words in the corpus. For example, the first sense, you contain a distribution over rat, cat, dog, etc. And if you look at it, you can think that okay, it's something related to the animal kingdom. And let's say there are k such ideas or senses in the corpus. Let's say Oracle has given us the sense pool. So now if a word bat comes, what I can do is I can take all the context words or the words that has occurred to the word bat in the entire corpus. Now it's a multi-set, so if the word cricket has occurred 3 times close to the word bat, I'll keep it 3 times in the multi-set. And I'll try to find those coefficients theta i's such that the linear combination of the senses kind of better approximates this multi-set in multinomial distribution. And I'll represent my word bat as a vector containing the theta i's. That's the generic idea of Word2Sense. So the contributions are twofold. First, I'll give you a single sparse interpretable embedding that contains the information of all the senses of a word in a corpus, and I'll use this sparsity structure and give an algorithm that refines the embedding dependent on the context. The evaluation is that okay, we beat the best unsupervised embeddings in Word2Sense disambiguation tasks, and we are competitive with the state-of-the-art models in other downstream tasks. Okay, so now we'll speak about the assumed generative model, and that will kind of imply the Word2Sense construction. Okay, so we assume that we are given this sense pool containing k senses, and each sense is represented by some of its stop words. We are also assumed that we are given the theta i's, that is the prior probability of each sense for the word bat. And now what I want to do is I want to generate the context around the word bat. So first position, I pick my sense 2 with probability theta 2, and I pick the word nixious from this sense. The second position, I pick the word eat from the sense 1, which was picked with some probability theta 1, and so on so forth. But why am I even caring to go context by context? Why not I join them together and form somewhat called a contextual ensemble? That is, it's a collection of all the words that is occurred close to my word bat in the entire corpus. Now, why? Because if each context is a linear combination of the senses with the same coefficients theta I, then the collection of all of them will also contain the same theta I as the coefficients, right? So, okay, so now what I try to do is I try to write the generative model formally with some dedicated prior for the sense pool distribution and the theta distributions. And as many of you might have seen, this is the LDA model, LDA generative model. So I can use some LDA inference model out there to generate my beta and theta. Okay, so what I do is I am given a corpus, I generate all these contextual ensembles for each word, pick a LDA inference model and run the LDA inference model on this set of ensembles, generate the sense pool beta and the sense distributions theta for each word. But after that, we follow some pre-processing steps so as to enhance the performance of our embeddings. For example, we give the information, we add some information from the sense pool beta to our sense distributions theta. We cluster some of the senses together to remove fine-grained senses. And third, we try to sparsify our vector by removing the heavy-tailed noise numbers and renormalization. Now that gives us some 3% sparse theta vectors. Okay, so the final theta vectors that I get is the embedding that I use for each word. So now I'll evaluate Word2Sense. But before that, let's check what the top senses that I captured for each word. For example, for a word like tie, I get senses like one, some activity related to a rope, second, some clothing material, and third, some result related to a football match. But the most interesting word was the word cell. Now this word can contain more than 5 different senses, which Word2Sense was able to capture, but multi-prototype embeddings couldn't because the number of prototypes were restricted to 2 or 3 for them. Okay, so Word2Sense kind of captures more senses than its other competitors. Okay, now let's see how it performs in similarity tasks. So the task is simple. You have to compare 2 words and say how similar they are. For example, friend and companion, they are similar. Men and air, they are not. So we compare 2 Word2Sense vectors using JS divergence between them, and other embeddings use cosine similarity. And there are different data sets to see how good we are in this task. Turns out Word2Vec is the king here, but we are not far behind. There is another task called entailment task, where we have to say if one word is a kind of another. For example, cat is an animal, but animal is not a cat. And there is a data set given by Baroni, and the Gaussian models Word2ZM were actually prepared for performing this task because Word2Vec couldn't. We use scale divergence between 2 Word2Sense embeddings to say how much a word entails another word, and turns out we kind of beat the Gaussian models in this task. The next task is the interpretable task, where we are given a set of 5 words and we have to pick the odd one out. So what we do is for each dimension we take the top 4 words depending on how much weight they have in the dimension and add an intruder word to it, and we ask the judges to see which one is the odd one out. So we had some 300 questions and we asked more than 3 judges on each question, and turns out 75% of the questions were actually answered correctly by our judges through majority voting, which is kind of close to the state-of-the-art interpretable embedding spine. Okay, so now I have given you some embedding, and I will give you an algorithm that uses the structure of this embedding to give you a refinement depending on the context. Why do we need that? So, for example, you are given a word bat, and you are given a sentence in which it occurs. I want to infer the meaning of the word bat using only the context words, right? Using only the sentence words. Now, what's the the idea that comes to the mind? Just use some LDA inference model. Does it work? No. Now, the reason that it doesn't work is because you're trying to infer the sense of some 10-15 words against an entire pool of 3000 senses, which is kind of difficult for any LDA inference model. But if you kind of think now, you actually want to infer the meaning of the word bat, right? So, but it has only a subset of some 20-30 senses that's relevant to it in the entire pool. So why not we try to restrict ourselves to this subset while inferring the sense of the 10-15 words we have. Now that's the major idea that we are moving forward with. Okay, for that we need to give you some new inference algorithm. Okay, so let's say we have this sense pool which is given by the matrix beta, which has been inferred using an LDA inference model on a huge corpus. Okay, we are given this set of sentence words. What we are trying to do is we are trying to find a linear combination in terms of the coefficients theta I. So we'll try to give a loss function that has two parts. A, it contains a log likelihood loss function between the predicate multinomial distribution and the multiset, and second, it contains some regularizer that kind of restricts our movement to the initial iterate theta 0. Now I'll try to explain why I do this in the next slide. So we have this situation now. We have the word bat, we have the sentence, we want to infer by restricting the number of senses to the senses that's relevant to the word bat. And in other words, we want to find the best possible theta I, that's a linear combination of the senses that best predicts the linear combination of senses of the multiset. Okay, but what I do is when the word bat comes, and let's say S2 and S3 were the only relevant senses for the word bat, I will try to restrict my focus only on theta 2 and theta 3, and others should be 0. Right? So, is it even possible? Turns out it's possible because if you recall, the Word2Sense embedding only contains non-zeros in the relevant senses only. So my word bat will only contain non-zeros in theta 2 and in second and third dimension, and others it will be all zeros. Right? So I start my optimization with the Word2Sense vector of the focus word, and then I try to run a multiplicative weight update algorithm. Now why? The name is the resolution is the name itself. It's a multiplicatable algorithm. It will only change the non-zero values. So the subset of optimization or the domain of optimization kind of stays the same throughout the training. So the final iterate theta t that I get can be called the word context to sense, or the refinement of word to sense, or the focus word dependent on the context. So how does it perform? In the first task, we are given a set of sentences and we want to cluster them into clusters where the focus word contains the equal sense, and that's called the Word2Sense Induction task. Okay, and there are two measures that measure how good your clusters are. For example, even if are you even predicting the true sense or the true clusters, or how diverse are your clusters? Right? And turns out we beat the unsupervised models out there in both the measures. Right? The other task is the SCWS task, where we have to compare two words in the respective contexts. For example, in this context, the word bat and dog both mean an animal, but here the word bat and dog mean different. Bat means a sporting sense and dog means an animal. So given a pair of words in the respective contexts, we compute their word context to sense vectors and then compare them with JS divergence. And there is an entire data set which tells how good we are in this task. Turns out the multi-prototype embeddings are still the best in this task, but we are not far behind. So in short, we give you an embedding that's competitive in downstream tasks like similarity, entailment, is interpretable, and we use this sparsity structure to give you an embedding that modifies the embedding depending on the context. Okay, future work. We couldn't perform well in analogy tasks. Can we do better? Second, it will be better if we can also give the representation of a phrase or sentence in the same model. And third, currently we are using some heuristic to come up with the number of senses in the corpus. Is it possible to automate that? So our code is available in my GitHub page. Thank you.